Hi everyone, welcome to Organic Insight. In this particular video, I am going to teach about SN2 reaction, that is substitution nucleophilic bimolecular reaction. I already uploaded a video regarding SN1 reaction, that is the link I will give it in description. Suppose here I will start with SN2 reaction example. I can give it as a tertiary. Here in case of SN1 reaction, we are taking tertiary carbon. Here I will have to consider a primary. Suppose methyl halide. I can methyl bromide as an example. I can treat this one with hydroxide ion. I will end up with a product with inversion of configuration. This is OH plus, this is bromide ion as a leaving group, or this is the first example, and as a second example I can add OTS, that is tosylate group, which can attach it to primary or methyl group like this CH3. Suppose here I can take it as S minus, sulfur as a nucleophile. Here I will end up with something like this. Here methyl group will be there like this, and here SH group. Here what is the leaving group? Tosylate, that is O minus like this. These are the two example of SN2 reaction. We'll start with the general reaction. How we can represent a reaction of SN2? I can write it as here R, here R dash, and here R double or R prime we can call, and R double prime, and here X as a leaving group if it is there. What will happen if I add a nucleophile, that is I will represent as Nu minus with lone pair. I can write it as like this. And what will happen, this nucleophile will attack this particular carbon and the leaving group will leave that particular carbon. I will end up with like this. Here R will be there, and here R prime, and here R double prime, and here nucleophile as it is like this, plus X minus, that is halide ion will leave as a leaving group. Now I will concentrate on mechanism. It is very important to learn about the basics. Now this all the process will take it in one step. Now I will consider a stereo, with stereochemistry I will write like this, and here halide group is there, that is X. I will represent halide or any leaving group. Here R prime, suppose here I will consider it as R, and here R prime, and here R double prime. Now what will happen, we added a nucleophile, that is Nu. I will represent this having a lone pair, correct? Now we know that suppose if carbon and halide, that is leaving group, if it is there, we know that this is a bonding molecular orbital, and exactly opposite of that we will have a anti-bonding orbital like this. And what is this called? This is sigma star, correct? This is anti-bonding orbital. If carbon and this halide bond has to break, the nucleophile is there, nucleophile has to give the electron to this sigma star anti-bonding orbital, so that this bond will break like this, correct? This one will happen, this exactly the same case it will happen in the above mentioned mechanism. I will represent the anti-bonding orbital in like this. This is the anti-bonding orbital. I will write it as antibonding orbital, that is sigma star of carbon and halide. I can write it like this, correct? Then what will happen if it donates a lone pair to this, and this bond also has to break like this. That's why here I will write it as arrow mark, and here I will write it transition state, something it will look like this. Here R, and here R prime, and here R double prime, like this. And here this is the bond which is showing away from the observer like this. And now I will show this bond as something like this is a point like this. This represents the bond is, this bond is going like it is breaking, correct? And here I will represent nucleophile like this. If it is leaving, this halide is leaving, it is carrying positive negative charge with that. That's why it is having delta negative. This one also with two electron, that is one lone pair it is entering, this is also minus charge is there, and overall I can represent it as transition state like this. Now if we observe this particular carbon, here it is attached like 5 bond we can see, that is 3 normal bond is there and 2 partial bond is there. Because of this 2 partial bond, what will happen, this carbon is electronegative in nature, that means electron deficient, electron deficient, correct, like this. And what will happen in the next case is this bond will complete, it will form the nucleophile and carbon and living group completely it will break, and I will get it as a nucleophile attached to carbon like this, and here I will represent R group like this. Here normal as it is, with inversion of configuration I can represent the product like this. Here R double prime like this, this is the product. Now we will discuss about on what condition, this reaction is called as bimolecular. Why bimolecular? In SN1 reaction we saw that the whatever the reaction is there, it is unimolecular, but this SN2 reaction is called as bimolecular reaction. That means when we plot a graph of, here rate is there and here concentration of carbon skeleton, here example I will take it as a methyl bromide, I can take concentration of methyl bromide. When we observe this one, the concentration of whatever the reactant is there, it will linearly, it will depend on the carbon skeleton actually. And also when we plot a graph of a rate on y axis versus here concentration of base or nucleophile, that is here I will take it as NaOH, this one also like linearly it will depend. Because of both rate equation we can write it as, I will just, rate is directly proportional to concentration of methyl bromide, that is CH3Br, and concentration of NaOH, correct. This is the equation, rate equation we will get. It depends on both the carbon moiety whatever it is there as well as the nucleophile. That's why this one reaction is of order is 2. Because of this we will call the SN2 reaction as bimolecular reaction. Then we'll move on to the next thing. This is the mechanism like in with respect to orbital interaction. Here you can see here methyl halide, suppose X is leaving group such as OTS minus or fluoride, bromide, better we can take it as iodide, like that we can take. Here you can see this is the empty sigma, sorry, sigma star orbital of carbon and halide, whatever it is there, bond. This nucleophile is interacting with this, and then this leaving group is about to break, and this nucleophile and carbon bond is about to form. This is the transition state, and here new bond, completely new bond will form. This diagram I have taken from the Claydon book. You can refer to that. Then we'll move on to the next thing, that is energy profile diagram. This is energy profile. Here you can see that we can observe when we plot a graph of energy versus reaction coordinate or reaction pathway, we will get a transition state that is only one, that is transition state 1. Whereas in case of SN1 reaction, we will get a 2 transition state with 1 intermediate. Here we can't able to observe the any intermediate, only transition state, that is higher energy state. Here is the starting material, and which one will form a simultaneous bond, like 5 bond it will form, and finally the leaving group will leave and nucleophile will form bond. Finally we will get like this. Then we'll move on to the next thing, that is like this. Suppose if adjacent carbon-carbon double bond or carbon and oxygen, that is carbonyl pi system is there, increases the rate of SN2 reaction. But how? Allylic compounds means, suppose this is a double bond is there, this carbon is called as vinyl carbon and this carbon is called as allylic. Suppose if attached something living group, this type of system we will call it as allylic. The same case it will happen in case of benzylic also. This statement is valid for benzylic carbon. This is phenyl group, this is phenyl group, and this is benzyl group. Suppose here halide is attached, this is benzyl group. Here also adjacent like this, here you can see that allylic system is also there. Just because of this is a benzene ring or phenyl, we will call it as benzylic. Allyl compounds or benzyl compounds reacts rapidly by SN2 mechanism because the pi system of adjacent double bond can stabilize the transition state. Here I used one term, this carbon is electron, this carbon is electron deficient, correct, because it is forming 5 bonds actually, like 5, not actually 5 bonds, but it is simultaneous. Okay, 5 bond type we can call it as, because the breaking is also there and forming of new bond is also there. It is forming okay, here I am not telling about these 3 bond, that is carbon and hydrogen bond. If I talk about only these three, if I talk about this, here carbon is having a 2 electrons like this, but it is forming a 2 bond. It is electron deficient we can call. What will happen if carbon is electron deficient? Here this carbon is electron deficient, correct? Suppose if a pi system is attached, then what will happen? This can, by resonance it will help like this, or with a like adjacent lone pair is there, that one also can act, or plus I effect, it will increase the rate of reaction. In such case what will happen? Plus M effect, that is mesomeric effect, will help the transition state to stabilize. If a transition state will stable, then the reaction will go forward. That means rate of a reaction will increase. Exactly that one we can see over here. This is the empty orbital or electron deficient carbon is having a p orbital like this. What will happen? This orbital will overlap, the transition state will conjugation with allylic pi bond we can able to observe over here. And the next next topic is, we can take it as a alpha halo. This is alpha halo ketones, or simply carbon, alpha halo carbonyl compound you can take it. with all observed substrate, this alpha haloketone, whatever it is there, it is showing a high tendency of SN2 reaction, because here is the reason. We can observe alpha haloketone generally we will represent simply. I will take one example, general example like this here bromine. Suppose if it is there, what will happen? This oxygen is there having a delta negative charge, correct? This carbon atom is there, it is having delta positive charge. Because of that, this carbon is also having a delta positive. Why? Because this is further attached to this group, as well as the minus I effect of this bromine group. Because of that, what will happen, between this carbon and this carbon, it is very like unstable nature we can observe. Polar will distract away from each other. Exactly like that, what will happen, this bond is also like something, it is very unstable. If I add OH minus to this, what will happen? These are two options. It can attack to direct carbonyl group, or this one can attack to carbon, like alpha carbon it can attack. Suppose attack occurs at carbonyl compound. Here what will happen? Here we will get it as, I will write over here. Here I will get this O minus is there, and here Br is there, and here OH is there. This is the tetrahedral intermediate. Suppose when it electron will come back again, like this will happen. What will happen? We will get a reactant back. That means there is no use of this attack at this carbonyl group. It is no use is there, because it is reversible. We want irreversible process, that is when the reaction will happen at this carbon here. When OH minus will attack this position, the bromide ion will leave, and this carbon is attacked by OH minus. This reaction is irreversible reaction. Okay, this reaction will undergo SN2 reaction. Then we'll move on to the example. Here example I will take it as alpha bromo acetophenone, correct? This is attacked by a nucleophile, that is piperidine. Piperidine having a lone pair on oxygen, it will attack this alpha carbon, bromide ion will leave, and finally with transition state here, I have not shown, but it is understood that nitrogen, if it gives a lone pair, it has having a positive charge, then charge nullification will happen, and finally we will end up with amino ketone. Now we'll move on to the next thing, on which case, sorry, relative rates of substitution reaction. Okay, in case of SN1 reaction, we observe that tertiary moiety, whatever it is that is showing high tendency of reaction, but here the steric factor will matter more. Here simple methyl chloride, it will show a relative rate, okay, 200 is more than sufficient, it is showing a high rate because it is least hindered by alkyl chloride. Then if it is secondary, steric hindrance will happen more because two large methyl group is there. We can observe the rate, it is decreased. In case of allylic and benzylic, we already discussed. It is showing between allylic and benzylic, the benzylic is showing more tendency of SN2 reaction because of more resonance. More resonance will happen in case of this benzyl group, correct? Like this. Suppose here positive charge is there on carbon. In case of SN1 as well as SN2, the same case, benzyl group will show a high tendency. Then we will have like this moiety, that is conjugation with lone pairs accelerate reaction. But okay, in SN2 reaction also it will show very good reaction, but majority it will happen through SN1 reaction. Now this one we just now we discussed, that is alpha chloroacetophenone. It is showing a very high tendency of SN2 reaction. Then we'll move on to the next thing, that is electronic factors. Okay, I will first discuss the stereochemistry. Afterwards, I will discuss electronic factor. Stereochemistry. For example, I will take a chiral carbon, that is hydrogen. Here deuterium I will take, here tritium I will take. This one attached to some bromine molecule, sorry, bromine atom. Then here I will add a nucleophile, that is hydroxide ion. Hydroxide ion will attack from backside like this. Here I will end up with here hydrogen, and here deuterium, and here tritium, and here I will end up with OH. Suppose this whatever the starting molecule is there, if it is of our configuration in stereochemistry, we will end up with the S configuration. Suppose here if I take S configuration, I will end up with R configuration. What is happening here? That is Walden inversion. Exact reversal of stereochemistry we can observe over here. And if I look into electronic factor will come under, if suppose benzene ring is there, here I will consider a benzene ring like this. Suppose this one is attached to methoxy group, and here we will have this carbon is we are talking about. Suppose if it is attached to bromine, then what reaction will happen? And suppose this benzene group is there, and if it is attached to electronegative group, that is nitro group, here what reaction we can observe over here? It is having positive and this is negative charge. This is benzyl group, here it is attached bromine. Okay, these two case I will take an example. Here what will happen? On oxygen we have two lone pairs, it will show plus M effect, correct? Because of this plus M, what will happen? Electrons, it will move like this, and here like this, and like this will happen. This bromide ion will leave, minus Br. Then what we will get? We will get something like this. Here Me group is there, positive charge on oxygen, and one lone pair is there as it is, and here double bond like this we will get. Now what will happen if I add OH minus as a nucleophile? This nucleophile will attack this particular carbon, and regeneration of aromaticity we can observe over here like this, and I will get a final product like here OMe group is there as it is like this, and here OH like this. Here what is happening? The intermediate we can observe here, that is oxonium ion. It is there over here. That means here SN1 reaction is going to happen. And what about in this case? Suppose here there is no plus M effect is there. Here minus M effect is there. Because of that, what will happen? This can't able to leave bromine as a bromide ion, it can't able to leave the whatever the substrate is there. Instead of that, OH minus is there, it will attack the benzylic carbon like this, and simultaneously the bromide ion has to leave. It will go through SN2 reaction. It is substitution nucleophilic bimolecular reaction. Because if it is happen through SN1 reaction, here we will get a positive charge on this, and this is electron deficient group. It will pull the electron, that is minus M effect it will show, which will destabilize the benzene ring. Because of that, it will not go through SN1 reaction. Instead, it will go through SN2 reaction. I can write it as a NO2 group as it is, and here OH. Product we will get here OH only, and in the first product also here OH is there, but through what mechanism it is going, that is very important. And here we can observe the relative rates with respect to water, that is with water the reaction is only 1 of reaction with Me, that is methyl bromide in ethanol. This is the nucleophilicity they are giving over here, and the pK value of the corresponding whatever the conjugate acid is there. In case of this, the pK of water they have given over here, and here phenol, that is PHOH. Here acetic acid, correct, and here that is hydronium ion we can call, and here perchloric acid, that is HClO4. They are given the pKa of these things they are given. We can observe over here, that is pKa, if it is very high, high pKa means the relative rate is also very high, correct. This is we can observe that what is the inference of that. That means the high nucleophile, if it is there, we can observe the relative rate also. That means high nucleophilicity, suppose high nucleophilicity, which is directly proportional to rate we can call. This is the order. Then the same thing we can observe over here. Here what is there? pH S minus. Here sulfur is there and here oxygen is there. Only that is the difference over here. Here between the sulfur and oxygen, which one is the best giving group? That is less electronegative and more electropositive. That is sulfur is there. Sulfur is more nucleophilic. We can observe the relative rate is also more when sulfur is acting as a nucleophile. Here oxygen is electronegative group, correct. Next to fluorine, fluorine is most electronegative, that is 4.0 electronegativity, and oxygen we can get 3.6 like that, correct, 3.6. That is the second electronegative element. Because of that, what will happen, it have a tendency of holding the electron. Because of that, the nucleophilicity is less. Because of that, it will show a relative rate like less compared to sulfur. Then okay, if SN1 SN2 reaction already we discussed, any reaction is there where we will get a SN2 reaction? Yes, it is there. We will get in Mitsunobu reaction, Mitsunobu reaction, where the inversion of configuration will happen. Okay, I will write it as normal example. I will write here like this group is there, here R double dash. If it is there, here stereochemistry I am showing of alcohol. Reagents is dead, DEAD, that is diethyl azo dicarboxylate, and the second reagent is triphenyl phosphine. And nucleophile I have to use, I will use it as acetate ion, and we will get a product as with inversion of configuration. Here I have shown with dash bond, here I have to show with like this wedge with here O and AC is there. AC corresponds to here CH3 C double bond O like this. This group is called as AC in short form. Then we can find it in Finkelstein reaction. That is also an example of SN2, where we will normally we will take RCl. Suppose here I will take it as RCl. When will here acetone as a solvent I will take, this is acetone. Suppose here I will add NaBr, then what will happen? it is a precipitation reaction. Here R and here Br is there. This whatever the Cl is there, it will precipitate, like chloride it will leave, and acetone molecule will solvate this. This is a Finkelstein reaction. In upcoming videos I will try to discuss about all those, the mechanistic aspect. For right now I'm just telling Finkelstein reaction is also an example for SN2 reaction. I hope today this video helped a lot to you people. Thank you very much for watching.